Hi, I'm Fangyin from Princeton University. I will present our work on clutter detection and removal in 3D scenes with view-consistent inpainting. With the proliferation of RGB-D cameras, we can imagine a day when people can quickly scan their rooms with a phone and share the reconstructed mesh. However, the scene mesh is typically full of clutter objects that are not wanted. In this work, we define clutter as frequently moving objects. Given a scene mesh with clutter and the scanned RGB-D images, our goal is to produce a clutter-free scene. Our method is composed of two steps: clutter segmentation and 3D inpainting. The biggest challenge in clutter segmentation is that clutter objects are typically small tail objects. Taking this scene from ScanNet dataset as example, we can see the clutter objects on the tables are small and of various categories and shapes. To better segment small objects, we designed an area-sensitive loss that adds a weight term to the classical cross-entropy loss. The denominator Ni corresponds to the number of points of an object. A small object has a smaller Ni, which increases the weight Wi and the loss for the object. This loss is fundamentally different from class imbalance loss, because our loss is on an instance level to better segment small objects, regardless of the class. The hyperparameter k controls the strength of weight. For smaller objects, a larger k increases Wi and the loss penalty. When k equals 0, Wi is equal to 1. The area-sensitive loss takes the same form as cross-entropy loss. For 3D inpainting, semantics and geometry are highly entangled. Simultaneously inpainting both is very difficult. To address this challenge, we propose to project the 3D clutter predictions onto 2D and leverage the powerful 2D inpainting models. During the separate RGB and depth image inpainting, we first inpaint each RGB image. Then, the inpainted RGB image is used to guide depth completion. We perform such RGB and depth inpainting for all views. Sometimes, the inpainted RGB-D images may not be consistent across all views. A direct reconstruction using these inconsistent inpaintings may easily produce artifacts. Therefore, we additionally perform view consistency checks and iterative refinement. Our proposed consistency voting and pruning significantly reduces artifacts. Finally, we reconstruct a clutter-free mesh using the view-consistent RGB-D inpaintings. Let's look at the full pipeline results on ScanNet dataset. These two images show the texture and geometry of the input mesh, with clutter objects in red circles. Our segmentation model is able to detect all the clutter objects. The next two images on the left are the texture and geometry of our output mesh. We can see that our method successfully inpaints the scene with plausible geometry and appearance. In comparison, the baselines either fail to close the holes or inpaint with oversimplified surfaces. We compare with two baselines, including Poisson surface reconstruction and hole filling algorithms. The results show that our method outperforms baselines on a variety of scenes. Next, we will take a closer look at the inpainting part and compare different scene inpainting methods. The first row shows the input mesh and ground truth mesh after inpainting. In the second row, we show our results on the right compared with two recent scene completion methods. Our method is able to better fill the holes and also inpaint with plausible appearance and geometry of higher resolution.